So I think we're on with the recording now. Like I said last week, and like I've mentioned in some of the other places, these sessions can take many different shapes. They are by no means required part of the course, but they're an additional resource that I do want to offer for my online students. So if you have burning questions, or if there's things that you want to discuss, or particular areas of the material from the week or even from the assignments, I'm happy to let the direction of the class to go to that direction. I don't have anything that's like that we have to absolutely cover. It really is these sessions to serve students and whatever students want to get out of those. However, if I don't have any questions, or if I don't have any students present with me, then I just normally kind of have a nutshell review of the main highlights of the chapter material on that week. So again, feel free to jump in at any point, but otherwise, if it's quiet, if I don't hear anything, I assume that we're on a good track, and I'll just kind of try to give a nutshell version of the highlights of this week's content. I normally spend a little bit of time also with my students checking how they're doing. I don't want to put you on a spot, but if you do feel like you want to indicate whether things are going really well or whether things are really, really rough in terms of this course, feel free to drop that on the chat or unmute. But again, I never want any student to feel that they're being put on spot. I also shared this with other students earlier on Wednesday of this class, that I am pretty big on the thinking that we shouldn't collect feedback from students only at the end of the class, or end of the semester, but we should be collecting feedback throughout the semester. So you can expect that in a week or two, I'll be sending out also kind of an anonymous survey where students can indicate what's working well, what we should keep doing, and maybe if there's something that we should be changing. Again, the idea behind that is that we can make changes during the semester, not only at the end of the semester. I've thought for quite a long time, there's many ways of doing this, and I wanted to be serving my students the optimally. So again, if you have something burning, feel free to share anytime, whether it's in this meeting, sending me a Canvas message, or dropping a chat, whatever of those works for you. Or if you want to wait, I will have that more formal survey as well available for my students. I'm going to skip today the portion where we do kind of a little bit more of an abstract reflections, how things are going. That's usually something that works better on a bigger crowd. Just as a reminder for anyone who's joining us through a recording, that these live online sessions at the moment, based on the kind of a little bit of a survey that we did at the beginning of the semester, we landed on Wednesdays 4:30 and Fridays 4 o'clock to have these sessions. Again, these sessions are fully optional. They're not required. The purpose is to provide many ways to meet many different learning styles of our students. So again, if it works for you, if you find it useful to join this, please absolutely do so. If you're busy, if you enjoy looking at recording, I know some of my students like watching those recordings twice the speed. I sound a little bit of like a chipmunk, but you also get through the material twice as fast. That's an option. Or if you don't feel like you need these sessions, I totally will respect that, and it's not something that's gonna upset me. Having said that, I do always give extra credit for anyone who joins these live online sessions, so you can expect as well to see that I'll add some extra points to your discussion forum later this week. So that's my incentive. So again, remember, my teaching philosophy is very much that I provide many ways of learning, many ways of earning points, and you do what works for you the best. We can visit the times and days if anyone has an interest. And absolutely, you do not need to have camera on. You don't need to unmute. I just want you to know that you let me know what works best for you. You totally can be however you feel comfortable. In terms of the recordings as well, I will always try to blur out the names of attendees and cameras of attendees once I've done the upload. But please do what's comfortable for you. So on that note, I guess that the biggest thing, since I'm a student myself, I always want to know how I'm being assessed. How am I going to get that good grade? Well, let's have a look at this week's material, what I'm asking students to do. This week, we're really covering only one learning module. In that one learning module, however, we're covering a bunch of chapters. We're covering chapter 2, 3, and 4. And it might feel like, oh, that's really cruel of me to throw so much material to students all at once. But quite honestly, I think that a lot of the content on these this week's chapters are things that students are already familiar with. The revision of your introductory biology courses, and that allows then us to make sure that everyone on this course is kind of starting at the same place. We have some students who have just finished their intro bio a couple of weeks ago. We have some students who have had couple of years since they took it. So we'll spend a little bit of time this week talking about basic chemistry of life, cells, tissues we spoke last week, and then we'll talk a little bit about genetics. The reason why it's important for us to know about those is that it's really what all of the subsequent chapters will build on. In the subsequent chapters, we'll cover one body system per week or per chapter, and really having that foundational knowledge is going to be helpful. So on that note, this week I have 2 chapter quizzes, chapter quiz 2 and chapter quiz 3. That I'm asking students to complete. I don't have any practice anatomy assignments since there's no new anatomy. This is just basic concepts. And then I have a discussion forum that covers all these 3 chapters. These 3 chapters and the discussion forum. Like I've said in the past, discussions can take many different shapes and forms. Again, it's about finding what works for each student. I want you to do what's beneficial for you. Some of my students opt out from participating at all for discussions, and that's totally fine. Some of my students go above and beyond on those discussions and can earn more than full marks for those. But the purpose of discussions this week is that we kind of try to shift a little bit, that rather than having just one single post, which is great that we get those single posts, we'll try to get a little bit more of a dialogue. So I'm looking for at least 2 posts from students who want full marks for discussion forum. And those 2 posts should be, the first one can be kind of a reflective and summarizing, but at least the second one should be in response to someone else's post. So we're trying to build that space where students can interact. You'll notice that obviously every teacher has their own thoughts, but we still work for an employer, and our employer is very, very eager of creating that culture of community in online spaces. So discussion forums are appearing across the board in many online classes with that hope that we can ensure that our students in online classes also feel that they have that support available. So those are the assignments that I'm asking my students to submit by the end of this week, which is Sunday, 1 minute before midnight. In addition, you of course have additional assignments you can do. You absolutely do not need to do those, but if someone feels like quizzes are not giving them enough challenge, by all means consider doing those want more assignments. Or if someone feels like they didn't quite score well enough in a quiz and they want to bring up their grade by doing additional work, that's available as well. But remember, you can try quizzes multiple times. Yes, that was fantastic what you have done. I'm just answering to a comment on the chat. You've done more than the minimum expected. So No, you have 2 posts in total. You've covered your bases. You're probably, if you've gone above 10 posting 2 posts, you're probably going to get extra points just for that. But this is perfect. So you can respond to me, you can respond to others. I normally am pretty active on the discussion forums that I tend to respond to students and then have follow-up questions. Sometimes that might feel a little bit of nagging. Don't feel obliged that you always have to answer to every question of mine. It's just giving those prompts that if someone is feeling like, I don't know what to say or what to write about. So you're in a great place. I also wanted to take this chance to kind of give a little bit of an idea of what's happening next week, not to stress anyone out, but because my teaching style, again, is very, very transparent. So I want to kind of lay out clearly what's coming ahead. So next week, we will move on to 2 new chapters. We'll cover chapter 6 and chapter 7. And on those chapters, we'll actually get to the actual learning material, get to the body systems in more detail. Kind of, I guess, the stuff that students signed up for this course and are really expecting. In addition to chapters 6 and 7 that we'll cover next week, students and me will be also taking our first tests. It's going to be exam 1 and it's going to be practical 1. And students are always nervous about those, and I totally understand. When I take tests as a student, I'm nervous as well. But let's start with a reminder that I'm not here to catch anyone out. I'm here to see every student of mine to succeed. Obviously, it has to be that we both put in a little bit of an effort. But to give an idea of what to anticipate that the exam 1 will cover, it will cover the first chapter that we covered last week. It won't cover this week's chapters, because I think that this week's chapters you've been already examined, and it might cover maybe chapter 6, we'll see. But it's gonna be, exams are always questions that are very, very similar, or if not exactly alike, the questions that you've seen on the quizzes. So doing weekly quizzes is the best possible preparation for the exam. And for the practicals are very, very similar as those practice anatomy questions. So again, doing those practice anatomy homework assignments is the best possible preparation for the practical. In exam, I do have a mixture of multiple choice, true, false, sometimes maybe fill in a blank or matching assignments, putting things in order, things like that. They're going to be completed on Canvas. And like I said, there's no curveballs, very similar, if not the same, types of questions as what you've seen on the quizzes every week. For practical, I show a picture of something as a question, and I ask you to tell me what it is that I'm showing. There's no physiology, it's just naming. That I'm glad to hear that that sounds fair and kind of doable. So there's going to be typically 4 options on a practical, and I'm asking which one of these is what you're seeing. So again, if you've done your homework, you already have prepared for the exams. Next week, I will also take time aside during our live online sessions to review for the exam and review for the practical. So there's nothing to fear, there's nothing to be stressed out, and the workload is doable. But I just, again, want to be fully transparent. Like I said, I believe that it's better to check facts as in medicine rather than guess. If I prescribe drugs and I don't remember the contraindications, and to be honest, those contraindications change every couple of weeks, I check it. I want to extend the same privilege for my students when it comes to exams and practicals. If you need to check something throughout that, you totally can do so. It's open notes. So let's not worry about the exam, let's not worry about practical, but I wanted to just kind of give an idea when people are planning their weeks ahead and kind of how to divide the workload. But as always, if anyone has any questions, feel free to just drop it into the chat or send me a message. Ask on a discussion forum. It is my commitment that I'll never blindside my students. I've been known to also say sometimes in my face-to-face classes that I don't think my students are ready to take an exam yet. So then we just push the exam back. I want you to be prepared and do well in the tests. But I hope that that kind of lays out what we're doing this week and what to expect from the next week as well. So if it's okay, I was going to give kind of like a nutshell version of the highlights of this week's chapters. As always, feel free to jump in, feel free to throw in comments, questions if something comes up. But in the interest of time, I'm just going to kind of move through it, try to keep up the speed. But if something needs to be expanded, I'm super happy to do so. Or if something feels too familiar, feel free to shout out that as well. So sometimes my students are confused. Why do we start anatomy and physiology course early on by talking about chemistry, that you signed up to biology class, not to a chemistry class? The reason is that really chemistry is what gives the basis for all biological reactions that we'll see. Whether we're talking of the very small scale or very big scale of studying biology, studying human body, we need to have a basic understanding of composition, structure, properties, behavior, and reactions of various different substances. So, for example, when we study physiology of various reactions, we need to go to we can go to very, very small scale to chemistry level to understand, for example, how muscle contraction happens. Same would go for anatomy. We can study cells, but we can go even smaller than cells. We can study anatomy of materials on the level of chemistry. So we'll do a general introduction to the chemistry just to make sure that we're all at the same place how we're starting. So when we're talking about chemistry, there's two terms that are going to come up, atoms and elements. And let's start with the elements. So elements are really what all living things are made of. It's the smallest level of studying materials that we'll be studying and that we can kind of get to with basic methods in a lab setting. We can actually go smaller than element, break apart elements, but that requires a little bit of additional effort and additional tools. So basic elements is about the level where we need to be. And what's interesting is that even though we have a periodic table of elements that we'll have a look in a little bit of, there's really only 4 main elements that are going to represent 96% of what human body is made of. So carbon and hydrogen are going to be the main elements that all organic chemistry is built on. So we often talk about, when we talk about organic chemistry, of hydrocarbon backbone of organic molecules. In addition, nitrogen and oxygen are largely represented in the human body as well. So those are the big ones. Those are the ones that we're going to keep an eye on. And those are the ones that are going to pop up often when we discuss about various different reactions, for example. Before we move any further, just kind of a reminder of a basic term of a matter. So when we're talking about matter, matter is something that has a mass and takes up space, so has a volume. So a good example is a pen that we might be holding. It has a mass. And when I use the word mass, sometimes students are like, why are you not saying weight? The difference is that weight is dependent on the gravity that we're at, whereas a mass is a universal term that we can use. So the weight of this pen will be different on Earth than what it would be on the moon. However, the mass of the pen will be the same regardless of the gravity. And the fact that this pen also takes up space, it has a volume. So that's what really defines something being matter. I often tell my students that they matter to me because they do have mass and they take up space. But really, when we're talking about elements, we're studying the smallest scale of matter that we can separate with basic tools, basic methods in a lab setting. Obviously, matter can take many different forms. I've highlighted there as an example. We'll talk a little bit later about water, why water is so essential for life. I've shown that water can take solid form as ice, it can be liquid, or it can be vapor like water, steam, or water vapor. Obviously, water is not going to take the fourth form of matter that only some elements have. Some elements can also take a plasma form. So I've added it there, but do remember that doesn't apply to all forms of matter. So now we've talked about the elements, let's have a look of the little bit of why this is important. So element was a pure substance that's kind of as clean, as clear as we go. Early on in the history of biology, in the history of study of biology, we didn't know all of the elements that we currently know. So the periodic table of elements representation of the elements was much more straightforward and simpler. But the reason why we've seen and why we've ended up with the periodic table of elements was actually initially the idea that students would not have to memorize, and people working on the chemistry field wouldn't have to memorize all kinds of elements. So I find it always entertaining, a little bit sad maybe, when I hear that some teachers make their students memorize sections of periodic table of elements. That's not what it's meant for. It's meant to be a resource that you can turn on to. And later on during this session, you'll see that actually how things are organized in periodic table of element is also very crucial. The location of each element gives us a very good clue of how they might behave in chemical reactions. So having that, referring to that, will allow you to predict largely what's going to happen in a reaction. So periodic table of elements, like I mentioned, not only do we have a listing of the elements there, often as abbreviations, as letters symbolizing those, and sometimes those letters, sometimes those abbreviations are very straightforward and make sense with English words that we use for elements. Sometimes they come from Latin or other languages, which might make it a little bit harder to kind of reason out that why is this letter pair symbolizing this element. In addition, we see a bunch of other information on each box, and we'll unbundle that in a second. And like I mentioned earlier on, we've been adding more information, more elements to our periodic table of elements. So it's been growing and it's been changing for a while now. So in this course, another term that will come up is, especially on the chapter 2, is the term atom. So atom is the smallest unit of ordinary matter. And that sounds very similar to the element. There is difference between element and atom if we really start splitting hairs, but for the purposes of this course, you can consider atoms and elements almost as interchangeable terms. And here is a diagram of what we often see when we talk about atoms and we try to understand what atoms are made. Because we can actually go smaller than just a single atom. We can break the parts or identify the different parts that atom is made of. So at the very center of an atom, you will see the nucleus of the atom. It's different from the nucleus of a cell, but it's a central part of an atom. Within nucleus, we will see protons, and protons carry a positive charge, and neutrons, which, as the name suggests, carry a neutral charge or don't carry a charge. So they're at the center of an atom. And then around the nucleus, we will have electrons that circle the nucleus. The number of electrons might differ depending on what atom we're looking at, but they always circle on a plane around the nucleus. You can consider it a little bit like our solar system where we have sun and then planets circle that. So the atoms would be circling the nucleus. And nucleus in this analog would be then our sun. We can also have these atoms just on one shell, or there might be multiple shells, so multiple planes that they circle. One thing that I want to mention when we're looking at this kind of a diagrammatic representation of an atom is that I don't want my students to think that this is actually as simple as what we're presenting to you. In reality, atoms are constantly changing. There's constant movement. Those electrons are moving, and they're not just on a two-dimensional plane. They're actually rotating on many directions. So even if you've looked at videos or illustrations how planets circle the sun, they're not all on a same level or same plane. They're moving all over the place. So much more dynamic than what these representations sometimes make us think. So I hope that kind of clarifies that. Really, again, I'm not trying to train you to be chemists. I'm simply trying to show the smallest level of that we're going to start studying of life. The important note is that electrons are negatively charged, and normally in an electronically neutral atom, we would see the same amount of negative charges as we see positive charges. And that will become important for us in a bit. So earlier on, I mentioned the periodic table of elements and how we see a bunch of information on that. And one of the pieces of information was the abbreviation or the symbol for that element. In addition to that, elements have their atomic number and they have their atomic mass often recorded. And sometimes my students ask that where do we get this atom's mass? Well, atom's mass is calculated by adding together the mass of protons and neutrons. Both of these represent relatively large masses in relation to the total mass of an atom. The mass of electrons is so insignificant that we just ignore that from that calculation. And again, some of this information might be useful if you're going to chemistry and you're really trying to unbundle and go to great level of detail of what's happening and what kind of reactions. So that's what I wanted to mention there. I also did want to, at this point, kind of challenge what I said earlier on and with my earlier examples. We actually see that not all atoms are alike. Even though it might be the same element, there might be differences within that element. And one of the kind of most obvious or most common examples that we use is that we might have a different number of neutrons in for that element in different atoms. So normally we saw that we had the same amounts of everything, but here we have two atoms. They're all in all aspects alike, with the exception that the neutron number is different. And this is what's known as isotopes of that element. And I guess, again, the question would be, why do we care about it? Well, radioisotopes are radioactive forms of an element, and they have allowed us to do some amazing things in the history of humankind, and also some pretty horrific things. So we've all heard about radioactive warheads, which the radioactivity then causes significant tissue damage, significant changes, radioactive pollution that stays around for a long time and can be a real issue. Similarly, in nuclear disasters like in Chernobyl, where we have nuclear power plant accident where the radioisotopes are released to nature, we still see even today consequences of that in the area, with forms of life being impacted, typically negatively, by the high radioactive landing of that disaster. In fact, we don't let humans go to these main sites of where serious radioactive pollution has been released. Or if humans go, they are very regulated how long of a time they can stay there so that it doesn't cause significant changes. But we use radioactive isotopes for a lot of good as well. And many of you are planning on going to medical fields. And I think that one of the best examples that I can think of, kind of relating to my own background as a medical imaging professional, is using radioisotopes as tracers. So there's something that we inject with a contrast to the patient during medical imaging, and they allow us to show what parts of the body, in this example, what parts of the brain scan, are most active during the activity that the person is doing while they're being scanned, or if we're just looking where there's more activity, where there's maybe more damage. That allows us to see local differences in the blood flow and either locate functions within the brain or locate where in the brain we're not seeing normal blood flow, and then figure out from that. Other way how we use radioisotopes that kind of relates to my previous background that I've mentioned briefly is in the history side of the house and studying archaeological findings. We can actually study from any organic material, do something known as carbon dating and figure out the age of the material that we're using. So we often use radioisotope determinations for that as well outside the medical. So that's why we talked about isotopes. Let's have a look at the periodic table of elements in a little bit more of a detail. Like I mentioned, it's very carefully thought out where different elements land on this table. And on this table, you'll see that the columns are known as periods and the rows are known as groups. And how these materials fall in certain periods or certain groups, again, helps us to predict the behavior of them in chemical reactions. Before we come back to that periodic table of elements, I just want to highlight some of the other concepts. Whenever we're talking about molecules, we're talking about a unit formed by two or more atoms. So when we don't have just individual atoms, but these atoms come together, they now make larger forms of material, larger forms of substances that we study, and these are molecules. And how these atoms are held together in a molecule is by chemical bonds. And we're going to be talking about different kinds of bonds that we'll see in this review session and in greater detail on your lecture material. One big thing to notice is that most molecules are electrically neutral. So overall, those pluses and minuses that we just talked about end up adding up so that there's the same amount of those. So I've kind of already touched upon this. So electrically neutral atom has the same number of electrons, which you remember were negatively charged, as it will have the number of protons, which were positively charged. So once we have minuses, we have pluses, and we have same amount of those, we end up with an electrically neutral atom. And this is going to be important once we start kind of figuring out how those bonds are formed. So let's unpack atoms a little bit further. Earlier on, we saw that atoms had nucleus, where we found elements as well. But now our main interest will be moving ahead, the electrons of an atom. And earlier on, we saw basically just one shell where these electrons were circulating. But in reality, depending on the number of electrons, we will actually see that an atom might have multiple shells. So again, think of those planets circling our sun. If all of the planets were on the same plane, it could be that there could be collisions. It could become dangerous. It could become an issue for us. So atoms are packed, or electrons are packed in an atom in a way, just a second. Sorry, I have a cat that's very needy for attention all of a sudden. So electrons are packed in an atom in a way that we can only fit so many electrons on each shell. And typically our interest when we're talking about chemical reactions is what's happening on the outermost shell. But before we get there, let's start unbundling the number of atoms per shell. So the innermost shell, the first electron shell that circles that nucleus, the maximum number of electrons that we can pack in there is 2. Then the second shell, the maximum number of electrons that we can pack in there is 8. And then if we have more electrons, we can add more electrons on subsequent shells. And we can have a number of different shells. But what we're really interested in, what you'll often end up seeing as representations on the chemistry descriptions, is only the outermost shell. because it is the outermost shell that's going to be responsible for reactions that happen. So we don't really need to draw these inner shells as long as we know what's happening on the outer shells. So the outermost shell is known as valence shell. And really what's going to be important for understanding the bonds that take place is understanding that atoms always want to end up to a stable state. So what atoms want to do, they want to make sure that their valence shell is full so that it has a maximum number of electrons that can fit into that shell. And if an atom gets to that place, it's going to be, if you wish, happy. So it's going to be then in a stable state. If an atom does not have a full valence shell, then it's going to be very, very reactive. It's going to be actively participating in chemical reactions. As you can see in this example, we have 7 electrons on the valence shell, and we would really want to have 8 electrons. So this particular atom would be very eager to take part in chemical reactions, whereas the one that we looked at previously that we see here had 8 electrons on its outermost shell, on its valence shell. So it's not going to be very eager to take part on chemical reactions. So I hope that that makes sense. So sometimes it might be that an atom wants to gain extra electron like we saw earlier on. That would fix the problem here. But sometimes it is that atom wants to get rid of electrons as well to get that full shell. Because if we get rid of this 1 electron on the valence shell, then this second electron shell becomes our new valence shell. It becomes our outermost shell. And you'll notice that there we have 8 electrons. So it would be in the stable state. It would be happy. So that's going to be important as we unpack a little bit how these bonds take place. So again, like I said already earlier on, getting that full valence shell is the goal for an atom. So based on this, now when we look at this periodic table of elements, we can see that the elements that are particularly reactive are found grouped together, and elements that are very stable are grouped together. And this can be explained based on the number of electrons that we see on their valence shell. So again, a chemist would simply look at an element on a periodic table of elements and be able to tell that, oh, this element is going to be taking part in a lot of chemical reactions, and this element is going to be really hard to make any changes on it based on chemical reactions. So let's talk about these chemical reactions a little bit. So earlier on, I showed this example. Chemical reactions, we can basically consider that something goes in, and something happens, and something goes out. And this was the example that I showed earlier on. We had an atom that had 1 electron on its valence shell. It was wanting to get rid of it. And once it gets rid of it, then it gets a full valence shell. So atoms are constantly rearranging themselves as molecules or as other structures, trying to reach that stable state. And the example of what I said that we have in chemical reactions, something going in, that is what's known as a reactant. And we have in chemical reactions something that is produced by the chemical reaction. That is what we know as a product of that chemical reaction. So reactants and products are going to be important for us to keep on mind as terminology, what goes in and what are we left with from the reaction, as these atoms are trying to, or molecules are trying to be formed in a way that they reach that stable state. Here I have a chemical reaction that's fairly common, and many of us probably know. So the reactants that we have going in are 2 hydrogens and 1 oxygen. When you combine 2 hydrogens and 1 oxygen, you're able to produce as a product water, so H2O. The 2 tells that there's 2 hydrogens and then 1 oxygen. So again, that's a good example of a chemical reaction. This type of a reaction is what we know as a reversible reaction when it can proceed to one direction only. So for example, if you take hydrogen peroxide, and many of you have probably seen that either if you're bleaching something like hair, or if you've been treating cuts on the skin, things like that. if you have hydrogen peroxide in a jar and you leave it to a room temperature or room conditions, over time, it will be converted into water and oxygen. So again, that's why I tell the people, if you're bleaching your hair, if you have a bottle of hydrogen peroxide, don't just leave it sitting on a counter and go do something else. You might end up with just a jar of water and the oxygen is now on the air. So in this example, the hydrogen peroxide was our reactant and the products were the water and oxygen. We see that in the chemical shorthand here that we actually have 2 water molecules that were produced for every 2 hydrogen peroxides. So this type of a reaction, like I said, was a reversible reaction. It moves only to one direction, from the reactant to the products. But we also have some reactions where it can move to both directions. So in this first example, the reactants that we have are bicarbonate and hydrogen. And bicarbonate and hydrogen can be converted into carbonic acid. But interestingly, carbonic acid can be converted also into bicarbonate and hydrogen. So this is what's known as a reversible reaction. It can go both ways. So where do we have a reactant? Where do we have a product? That might change and flip around based on the reaction that we're looking at that particular example. But in reversible reactions, we're moving both directions. Sometimes we have multi-step reactions as well. For example, bicarbonate and hydrogen to be converted into carbon dioxide and water requires an additional step in between. So bicarbon hydrogen is converted first into carbonic acid, which then can be converted into carbon dioxide and water. Similarly, carbon dioxide and water can be converted into carbonic acid, and that then converted further into bicarbonate and hydrogen. So we're seeing that these chemical reactions often are much more complex than we give them credit. So now that we've talked about molecules, we've talked about elements, we talked about atoms, we saw that molecules were made of multiple atoms. Let's have a look at that concept that I mentioned, that there's bonds between different atoms when we form molecules. And there's really 3 ways how these bonds can be formed. The first example of three ways of forming bonds that we're going to be talking about is what's known as covalent bonds. In covalent bonds, we're sharing electrons in order for all elements that make up that molecule to end up that happy, stable state. So in reality, actually, none of these is perfectly happy all the time or perfectly stable all the time, but most of the time, all parts of this molecule are in that stable state. So I often describe my students that covalent bonds are an example of the fact that sharing is caring. So in order to reach that stable state, that happy state, different atoms now end up having to share their electrons so that everyone gets what they want out of that being part of that molecule. So let's have a look at that a little bit. So here we have 2 hydrogens, 1 oxygen. They could join together to form a water molecule. In water molecule, let's have a look at that starting state. The hydrogen, really to reach that stable state, would want to get a second electron on its valence shell. And the oxygen, to reach that stable or happy state, it would need to get 2 electrons on its valence shell. An easiest way to accomplish this is to form a molecule where there's 3 players. There's 2 hydrogens and 1 oxygen. And these hydrogens and oxygens are going to share 2 electrons, so 1 pair. And each one of them is going to share that 1 pair. And this is really where you see the chemical shorthand. Sometimes when you see formulas written or molecule structures written out on the board, and you see that there's a line between the different letters that symbolize different elements. That line tells us that these atoms are sharing electrons. If it's a single line, it means that these atoms are sharing 1 pair, so in total 2 electrons. We can also see that often these illustrations are actually not as clean or beautiful, and they are actually slightly tilted. We'll unpack why we see this tilted structure rather than the nice 90-degree angle that we had in previous example. That is actually important, and that is going to be something that's fundamentally crucial for life. I also wanted to show another example of a covalent. Here we have two oxygen atoms, and they form a molecule of two oxygens. On each of these oxygens, we had 6 electrons on the outer shell, but how they can reach that stable, that happy state, is that they actually share each 2 pairs of electrons, so in total 4 electrons. Each pair is symbolized by a single line. So again, on those molecular formulas, if you look at the chemistry of a molecule and you see a double line, that lets you know that 2 pairs, so in total 4 electrons, are being shared between these atoms. So that kind of hopefully helps to make sense of something that you might have seen or you will end up seeing later on, what you're actually being shown. I also wanted to talk a little bit about polarity and non-polarity of a covalent. So when we have electrons that are evenly shared or equally shared between the 2 atoms that form that molecule, we describe this equal sharing as a non-polar bond. So remember, so far we've been looking at covalent bonds sharing electrons. This is a form of covalent bond that is known as non-polar because the sharing of the electrons is equal. So let's have a look now what a polar sharing would look like. In a polar covalent bond, the sharing is not equal. Actually, the electrons spend uneven amount of time between oxygen and hydrogen. Both are able to reach that stable state every now and then, but one of these is able to be more stable than another. So that's what we talk about as polar covalent bond. The sharing is unequal. And that unequal sharing often causes these shapes to be a little bit more abstract or a little bit more curved than what we would like probably to see as humans who like very clear 90-degree angles and so on. So we're seeing here our water molecule. In case of a water molecules, the electrons spend more time at this oxygen end than they spend at hydrogen ends. As a result, the shape of the molecule is this slightly tilted. And as a result, because of this uneven sharing of electrons, we talk about this kind of a molecule having polar covalent bonds. Sharing of the electrons is unequal. So that was our first type of a bond, our covalent bond. Now let's have a look at ionic bonds. Ionic bonds differ from covalent bond because actually we're not sharing anything. We're totally giving away electron or gaining an electron. So there's a complete movement of an electron in order for this type of a bond to be formed. And here I have a really good example of, again, what's happening early in the reaction and what's the outcome of that reaction. So here, the first atom that we see on the valence shell, so the outermost shell, there's a single electron. So this atom is going to be actively looking for ways to get rid of this extra electron, because if it's able to do so, as you can see here that it was able to do so, it's going to have then the new valence shell that's going to have 4 electrons on it. So it's a full valence shell, and it has now become stable atom. We have a second atom here, and we see that this atom has in total 7 electrons on its valence shell. In order for it to reach this stable state, this happy state, if you wish, it would really like to receive 1 extra electron. And in fact, that's what it did, as we see here at the end, and it now became stable. It reached a happy place. But whenever we're either giving away electrons or gaining electrons, remember that number of charges, number of pluses and minuses, is now not going to be even. It's not going to even out like we saw that was in an electrically neutral atom the case. So that's going to cause us that any atom that has lost electrons has now more positive charges in its nucleus than it has electrons. So overall, it has a slightly positive charge, and we call it a cation. Any atom that has gained electrons, it now has slightly more negative charges than it had positive charges in its nucleus, and it has overall negative charge, and we call it an anion. And what we see in ionic bonds is that positively charged cations are attracted to negatively charged anions. However, there's no sharing of the electrons. Electrons move completely, either giving those away or gaining those. But these overall charged atoms, they end up forming bonds based on positives being attracted to negatives and negatives being attracted to positives. So I guess that's the big story between behind the ionic bonds. And we see that many salts, for example, form these ionic bonds. The final type of a bond that we're going to be talking about is a hydrogen bond. And sometimes when I introduce these hydrogen bonds to my students, they're like, this sounds familiar. We've already heard about that. And that is the case. But we have grouped hydrogen bonds as a special type of bond because water is so important for life. So even though technically you could say that it's just a special form of ionic bond that comes as a result of covalent bonds that we see in water molecules, hydrogen bonds are their own group because water is so crucial for our life. So let's unbundle that a little bit. So like I said earlier on, the electrons were shared unequally in a water molecule, so that the electrons spend a little bit more time at the oxygen end than they spend at the hydrogen end. As a result, the oxygen end has slightly more negative charge than the hydrogen ends that have slightly more positive charge. So this is again a polar covalent bond. We saw that earlier on. Both hydrogens and oxygens reach that happy state, but I guess you could say that oxygen is getting a little bit more out of the deal. The electrons are spending more time there. So overall, even though the water molecule's charge was neutral, within different parts of the water molecule, there is unevenness in terms of the charges, with hydrogens being positively charged and oxygens negatively charged. This has important consequences for us, as we will see as follows. So here what I've done, I hope that this moves ahead. I've removed actually all other information and I've just redrawn that water molecule, kind of representing actually the sizes more accurately. Oxygen is a larger atom than hydrogen, and we see that oxygen as a result was slightly more negative, hydrogens were slightly more positive. So now we don't just see a single water molecule. Often we see a bunch of water molecules together. And these water molecules organize in relation to each other. And how they organize in relation to each other, so the negative ends of one water molecule are attracted to a positive end of another water molecule. So there's a careful way how water forms this larger mass of matter where the water molecules are organized in a particular way. What's interesting about hydrogen bonds is that, yes, we form these bonds, and in certain settings, these bonds are really, really crucial for water. And in certain settings, these bonds are very weak bonds. So we're going to talk a little bit about why water is so crucial for life. And that all comes back to these hydrogen bonds. So let's have a look. Often when we talk about life, when we talk about biology, we end up realizing that water is crucial. And even when we go to the space and we look for new planets and we consider could humans live in other planets, or if there has been other forms of life in other planets before, what we're really doing, we're looking for evidence of water. This is because as far as we know, all life requires water. There is no life without water. The reason why life requires water, we can kind of summarize those reasons, I guess, in 7 bullet points. properties. Let's go through those together. So first reason why water is so crucial for life is that water is a great solvent. Most things dissolve into water. And we will see this in chemical reactions. Oftentimes, when we do chemical reactions, one of the key things for us to do is to put water into there. We also see that in a human body that we dissolve things into water. Let's use blood as an example. Blood is largely water, and many things can dissolve into water, and that is going to be crucial for human body's function. Similarly, we see that water has two specific properties that we're going to talk a little bit more about next. First of these properties is that water molecules form cohesive forces with each other. So you remember how we just had that picture where we had multiple water molecules and we saw that they were attracted to each other. Well, this is an example of that in practice. Here we have a glass of water, and we filled this glass of water actually even higher than where the rim of the glass is. And rather than water flowing out of this glass, it starts to form this dome-like appearance. This is because these water molecules are holding to each other and not willing to let go. And as a result, you can actually overfill a glass without the water flowing out. And these cohesive forces are going to be crucial for many forms of life. We see that blood tends to stick together because the water molecules there like to remain connected. We see this even in the plants where if we have a good flow of water, that flow of water will pull the water behind it onwards. We'll unbundle that concept in just a second. But cohesive forces refer to the fact that water molecules were attracted to other water molecules. Then let's talk about adhesive forces. Adhesive forces refer to the fact that water molecules are attracted to polar surfaces. So some evidence of that we can see if we step outside on a morning and we see the morning mist on spider web surfaces of the plants. These water droplets are holding on tightly to these other substances, other materials. Another example that we see on this diagram at the bottom left corner, let's ignore what's in the middle and just look at this jar where we have water. Often that water tends to climb up on the edges of the glass. This is because these water molecules are holding on to that edge of the glass because of these adhesive forces. So they tend to stick to other surfaces and other surfaces that are especially polar. What we also see in this illustration is actually a really good example of adhesive forces and ties into something that I mentioned briefly earlier on. If you have ever been in a chemistry class, you've probably seen this experiment done where you have a jar of water and you have a very, very thin glass straw. When we put that very, very thin glass straw into a jar of water, the level where the water is lined or water is stabilized in that jar tends to climb higher in that glass straw. And that's because of the adhesive forces of the acting on that water in that narrow straw, pulling the water up against the gravity. And this is in fact exactly how plants transport water up against the gravity, even to high heights, many meters on some of the taller trees. So adhesive forces help us to pull the water up on a thin tube-like structure. And then that water that's coming behind is sticking together because of the cohesive forces of the water wanting to stay together. So two main concepts, and we see this not only in plants, but also in humans. Those two forces that interplay. Let's talk a little bit about kind of consequence of a cohesion. So this is just an expansion of a cohesion. And the doodling that you'll see at the bottom of the screen, we'll talk through that in a second. But first, I want to talk about what we see in the picture. So we see that often many bugs seem to walk on the surface of the water. This is because these bugs actually weigh less than what is needed to break these cohesive forces that we had for the water and the surface of the water. So breaking these cohesive forces is not accomplished because the bug is so light on its weight. Remember that glass where we had water and it didn't flow over because water molecules were sticking together. Now these water molecules are sticking together so hard that a light bug can just walk on the surface of the water. And this is exactly what we know as surface tension of the water. Now let's unbundle this. Where could we have seen examples of this a little bit more? If any of you has been in a water park and you've been jumping into the pool from various heights, you will have seen the surface tension at play. If you do a belly flop onto a pool, so you jump into it so that you hit the water with kind of a flat your feet first, it's gonna hurt. And the reason why it's gonna hurt is that you're gonna have a hard time breaking the surface tension of the water if you hit the water as a flat surface, large body that's flat. So therefore, what we actually often see people doing when they're doing jumping into water at the at the water parks, I guess, is that they jump into the water in a way that either their hands or their feet first hit the water and break the surface tension of the water. Once you've broken that surface tension of the water, rest of the body can follow, and it's going to be relatively easy and not painful. But this is why, as for having formerly worked in aviation, I tell my students always that sometimes landing on a big body of water in an emergency landing situation with the plane, it's like landing to a concrete. The surface of water can be really, really hard if you don't end up breaking that surface tension. If you do, I guess, with a plane, what you would be considered as a belly. So that's an evidence of cohesion in action as a surface tension. Let's continue talking about why water is so crucial for life. And we see often that many forms of life prefer to live by big bodies of water. So we see more diversity of the plants, more diversity of the animals, and even as humans, we tend to enjoy those properties that are located by the coastal areas. And that is because water has an amazing ability to bind heat and then release heat throughout the day. Let's talk about that a little bit. So here we see a diagram where the x-axis shows the time. So this is a single day that we're looking, what happens to the temperatures over the day. And the y-axis is the temperatures. So we're now early in the morning and sun comes up. And as the sun comes up and day gets warmer, the temperatures tend to rise. Then the afternoon comes and sun starts to go down as we're heading to the evening. The temperatures tend to drop because there's not as much sun anymore. And then comes the night and temperatures plummet. And then morning approaches again, sun is coming up and the temperatures start to rise. So we end up seeing that the temperatures throughout the day fluctuate. And that's normal. However, now, if you're living close to a coastal area, you will see that this fluctuation is far lesser than somewhere like, let's say, here in Arizona. So what we will end up seeing if you live next to a big body of water, that during the day when the temperatures are high, the big body of water, let's say it's a lake or ocean, it tends to bind some of that heat. So the temperature doesn't climb quite as high. And then during the night, it releases some of that heat so that the temperatures don't drop quite as far. This is why we don't see as big temperature fluctuations in coastal areas over the day. That's why big bodies of water are great examples of how water works as a great heat reservoir. Well, at this point, you might be asking, why do I care in terms of human anatomy and physiology? Well, you should care because we actually see your blood, again, as an example, is largely made of water. And since your blood was largely water, your blood actually is able to bind some of that heat and transport that heat to another body compartment where we can release that heat. I'm just going to make a quick note because I keep a record who has been present so I can give you extra credit. So just give me a second. Thank you for joining us. What we were seeing is that we were able to bind some heat with the water. And let's think of an example in a human body. Let's say that I go to the gym and I start exercising there and I'm using a lot of doing muscle work. My skeletal muscles are working hard. I'm running on a treadmill. As I'm running on a treadmill, I'm converting chemical energy into mechanical movement with my muscles. And as a byproduct of every time we convert energy from one form to another, we end up producing heat. And if I kept doing that, my core body temperature would keep climbing and I would overheat and eventually I would pass out. That's not ideal gym visit. Well, that's not going to happen. And the reason why that's not going to happen is that the blood rushing through my skeletal muscles, let's say that I'm on a treadmill rushing through my lower limbs, captures some of that heat and transports it at other body surfaces where I can evaporate, I can get rid of that heat without overheating as a whole body. The other example would be, let's say I go out on a cold winter's day, and during that cold winter's day now, first parts of my body that are probably going to get a frostbite are going to be my nose and my ears if I'm not properly prepared for that cold weather. Well, that's not actually going to happen immediately, as likely as it would happen, because my body will keep carrying warm blood from core of my body to those surfaces that are now having temperature dropping. So again, we're seeing that water and properties of water were crucial for us to navigate and keep the body temperature where it needs to be and at different parts of the body where it needs to be. So we started with a very general concept and now we're seeing it applies to human body. Let's talk about another important concept in relation why water is so crucial for life. Water is crucial for life because water can take many different shapes, many different forms. We talked about how water could be solid, it could be liquid, or it could be water vapor earlier on. So I'll just leave it to that. We've already touched upon that different forms that water takes. Final bullet point for why water is so crucial for life, really, I think, in my mind, ties into where we started our entire discussion. We started our entire discussion by talking that water is a great solvent. And what we see now is that because water is a great solvent, water is also an excellent transport media. So we're able to transport a lot of materials around our body in the blood because things dissolve into water, and based on that we can then transport those things in the body. So let's use blood as an example again. Many things can dissolve into water and many things can dissolve into the blood, and as a result of that we can use our cardiovascular system, our blood, to transport those things around our body. So those were the reasons why water was so crucial for life. A couple of basic terms that I want to introduce, and I'm introducing them mainly so that when we talk about cells, it makes sense. So we have certain substances that are known as being hydrophilic. These substances are attracted to water. And then we have certain substances that are hydrophobic. These substances avoid water. So remember, if you have a phobia, you try to avoid it. So this is going to be important later on as we talk about cell membranes and how cell membranes are formed. And all of this comes back to the chemical properties of a water molecule, this polar molecule that we talked about for the first part of the class. And here we see a really good example of this. So what we see is a small section of a cell membrane of an animal cell. So remember, your cells were kind of like, you could compare them like someone would have filled in a balloon with water. And that rubber part of the balloon is now the cell membrane that we see a cross section of here. Cell membrane is actually made of phospholipids. Phospholipids have a head part that's hydrophilic and tails that are hydrophobic. And because of this attraction of the heads towards the water and avoidance of the tails of the water, if you put a bunch of phospholipids in a setting and let them spontaneously organize themselves, they will form this double layer, which is known as phospholipid bilayer, that separates the inside and outside of the cell. So they form the cell membrane. If this feels vague, we'll revisit that once we talk about cells. Finally, a question about why does ice float on water? We get back to some of the basic properties of the water. Remember those water molecules and how they spontaneously organize so that the negatively charged parts of the water molecules were attracted to positively charged parts of other water molecules. So in liquid water, there's this very specific way of organizing these water molecules. Now, if we freeze water, what actually interestingly happens is that these water molecules have to be pushed further apart each other to form this ice crystal appearance of water molecules. So as a result, the same volume of water now expands to a larger volume as it freezes. And because you remember that this is now a larger volume, even though it's the same amount of water, it takes more space, so it's going to be lighter, it's going to float on surface of the water. This is actually exactly why you do not want to put glass bottles of, say, sodas into your freezer, because as the soda freezes, and soda being mainly water, as it freezes inside that glass bottle, it's going to start expanding. And if the container cannot hold its expansion, it's going to break, and then you have a whole mess in your freezer. Same thing, why during freeze nights we want to empty our water hoses, garden hoses from water, so that the water that's trapped in there doesn't expand and split our pipes or our hoses. So hopefully that kind of explains why water floats on the surface of, or why ice floats on the surface of a water. One more concept that's really crucial for us as we talk about basic chemistry, the pH scale. What pH scale tells us is the amount of hydrogen atoms in a solution. And pH scale ranged, we remember that 7 was kind of the neutral. And if we went anywhere higher than 7, we started talking about basic substances. If we went below the 7, we started talking about acidic substances. What sometimes trips out my students about the pH scale, and what I really wanted to highlight here, is that pH scale is actually not a linear scale. So in linear scales, we see that the relationship between values is, like the name proposes, linear. So you can say that 4 is twice of 2. Well, in case of a pH scale, which is a logarithmic scale, this doesn't apply. In logarithmic scales, it's kind of a curved trace that we see. And 4 is by no means twice that of 2. So there's a significant difference when it comes to that. It's not a big detail. It's not something you need to worry about, but I did want to mention that because that sometimes confuses my students. But the acidity or basicity of the substances is going to be important later on your course. I think in BIO202, especially when we talk about urinary system, regulation of your body pH and things like that. Interestingly, you do have chemicals that are known as buffers. And if you have taken BIO181 with me, one of the things that we do in a classroom is that we study different chemicals and find out which ones of those are good buffers. What buffers do, they neutralize either very acidic or very basic substances, bringing their pH closer to 7. And this is something that happens naturally in your body. I think a good example of that would be, for example, if you have a tummy ache and you then take Tums, that Tums neutralizes the acidity of your stomach contents so that you don't get that really acid reflux and burning feeling. So buffers help us to neutralize the pH fluctuations. And really, to put it all together from chapter 2, what we end up seeing is that organic chemistry, the chemistry of life, really refers to any chemistry of materials that have living origin. So the organic chemistry, those materials have been either they're living or they have been living. Organic chemistry was based on carbon and hydrogen, so hydrocarbon backbone, and we then see that in that long chain of carbons that have joined, carbon atoms that have joined together, we have functional groups that are added. Interestingly, what we see here is highlighted different arrangements of carbon atoms joining together. Now you know that a single line meant that a pair of electrons was shared, and a double line meant that 2 pairs of electrons were shared. What's kind of cool, what you are able to see on these examples that I picked, that we have same number of carbons on all of these molecules, yet these molecules look very different. So we call these as isomers of the same molecule. They have same chemical formula, but they take very different physical forms. So that's another term that you'll keep running into and you keep knowing. And I mentioned those functional groups that then intend to join to this hydrocarbon backbone. I have a handout of those on your Canvas course. I don't expect you to memorize those, but they're there if you're interested. What's interesting about functional groups is that they behave chemically always the same way. So once you get further into chemistry and you keep seeing functional groups being added to your hydrocarbon backbones, you can predict again how that molecule is going to behave in a chemical format. So that was our chapter 2. I do realize that it's been already a long session. If anyone needs to go, as always, feel free to jump in and jump out. If we don't have questions about chapter 2, I'm just going to keep soldering ahead and I'm going to move on to chapter 3, the highlights from that. But again, remember that this is as much or as little as you wish. I appreciate you being here. You'll get your points for having been present. But again, I think that it's going to be useful to go through chapter 3. So when we start going through chapter 3, what we see is that we're again faced with the familiar term molecule that we started with. So remember again, molecule was when we had 2 or more atoms that came together and formed a substance on their own. So we're going to be looking at 4 main molecules. We're going to be talking about carbohydrates, lipids, proteins, and finally a little bit about nucleic acids. These are known as macromolecules. So they're very large molecules, and they're actually molecules that all life is based on. There are also things that you see that we can also see in food products. People are worried about what macros they consume. Before we start talking about those, I just want to get a language set up for us so we know what we're talking about. When I'm talking about a monomer, I'm talking of a single unit, a single molecule of a matter. Here we see a glucose molecule. So it's a monomer of glucose, a single sugar. When we have multiple of these units that have joined together to form a longer of a chain, we're talking about polymers. So polymers are chains of many monomers that have joined together. So they're far more complex. How these are formed is through 2 processes. And the first process that we're going to look at is dehydration synthesis. The word synthesis tell you that we're making something new. So we're making polymers out of monomers. And how we do polymers out of monomers, how we synthesize polymers is through a dehydration reaction. So as part of this reaction, water is being produced. So that's all it tells you, that dehydration synthesis refers us taking individual monomers and joining them into a polymer. As a byproduct, water is being formed. The opposite reaction of that is what's known as hydrolysis. Lysis refers to breaking apart, and hydro again referring to water. So by adding water into a polymer, we can break that polymer apart into individual monomers. sugars. So that's what we're seeing there. And we actually see this interplay going on. If let's say that I take a glass of water and I put sugar cubes in there, those sugar cubes will eventually break apart. We will do our hydrolysis due to the water being produced. And then if I evaporate all of the water out of that mixture, we then start forming polymers in dehydration synthesis as a result of that. The sugar tends to crystallize in a glass. But really, I just want you to know the terminology. I don't want you to worry too much about that. I also wanted to introduce a chemical element known as enzyme. Enzymes assist you in various reactions in chemistry. So the assist can mean many different things, but these are chemical reactions that would already happen, but by adding an enzyme to it, the reaction just happens much better. So let's have a look how that assistance can happen. So that assistance can be that it makes the chemical reaction faster. It can be that it makes the chemical reaction easier. Let's say, for example, that the activation threshold that we need for that chemical reaction is lowered, or it makes that reaction more complete. So there's many ways how enzymes can help chemical reactions, but the key is that they assist us in those. And if you've ever wondered what an enzyme would look like, here's one illustration. So we have our initial enzyme and we have the material that we're dealing with. This material would anyways already be broken into two pieces, but by adding enzyme to this reaction, the material has to bind to the active side of an enzyme, then the enzyme's shape will actually change as a result of that. An enzyme will help to do this reaction, and once it has done the reaction, it returns back to its original shape, so it can be reused again to assist with further reactions. I think the most common example of enzymes that your textbook loves to talk about is catalyst. Catalysts speed up chemical reactions, so they make those chemical reactions happen much faster. Your textbook kind of incorrectly claims that all enzymes would be catalysts. That's not the case. We have other ways how the enzymes can assist chemical reactions, but one common way is that they work as catalysts. So now that we have this language, we can really start unbundling these macromolecules that are foundation for life. Let's start with carbs. And when I speak to my students about carbs and where you get carbs from in a diet, they always tell me flour, potatoes, rice, pasta, corn. But there's so many other sources of carbs as well, vegetables, green stuff, a lot of other sources of good carbs. And why we are attracted as humans to carbs is that carbs provide us not just energy, fuel to drive our body processes, but also raw materials to build our body, build structures in our body. So I think that that's why evolutionarily we enjoy eating carbs, because when we were hunter-gatherers, when food was short in an evolutionary history, there wasn't that much food available. There wasn't that much raw materials available. So when we got some, we really wanted to consume it. Well, now as modern humans, we're not really short of carbs around us, but we're still attracted to eating those. Other thing about carbohydrates can also contain fiber. Fiber is the non-digestible element of that carb. Getting fiber in your diet is really important. And the reason why it's important is for really two main reasons. Fiber gives bulk in your digestive system, so makes you feel full. If you eat foods that don't contain fiber, your stomach, which actually tells to your body whether it's full or empty, operates partially through stretch receptors. If it doesn't get stretched, you just keep eating and eating. But by having that fiber in your diet, your stomach stretches, and all of a sudden you feel, oh, I'm full, my stomach is full. What you fill it with is important in terms of your diet. The other reason why fiber in diet is important, that fiber really helps to push the material along the digestive tract. So it helps kind of to scrape the edges of the digestive tract, material moving there, helps to clean the digestive tract, keep it working nicely. So now let's have a look at different kinds of carbs that we have. We have monosaccharides, which are just simply made of simple sugars. We have disaccharides made of two sugars, and then polysaccharides, which were made of a chain of many, many sugars. And my students always ask me that which ones of these should I be eating? Should I be eating complex sugars or simple sugars? And I guess one way to look at it is, if you have kids, you notice that when you give kids foods that contain a lot of sugar, so very simple sugars, candy, things like that, they get a sudden burst of energy because now they have all this energy available in their body. But very soon, they will also get that sugar crash once that energy has been burnt off and they run out of steam, so to speak. So that is the reason why we encourage people, if you're going to eat carbohydrates, probably consider opting for complex carbs. Those complex carbs need to be broken down into simpler carbs, and this process allows those complex carbs to be around in your body for much longer of a time, so you don't get that sudden crash. So really the sugars, the source of energy, is available for your body when you need it if you eat more complex carbs. This slide, I was debating whether to even include it. Chitin is one type of a polysaccharide. It's polysaccharide most bugs that have an exoskeleton, the exoskeleton is made of. So unlike humans who have internal skeleton, many bugs, many insects tend to have an exoskeleton. I compare it to my students, consider kind of armor of a medieval knight, but that being your skeleton. You don't have bones inside. And actually some bug sprays work on dissolving these chitin polysaccharides, and that's what's the death of those bugs. But that was just a side note that I decided to include. And I think we already discussed about the importance of consuming rather complex carbs than simple carbs as a way to really provide that a source of energy and nutrients for a longer time in your body. And that brings us to the second macromolecule that we need to talk about, which is our lipids. Our lipids are our fats. So when I talk about dietary lipids, my students always tell things like butter, lard, oil, things like that. But there are other sources of lipids as well that are considered as healthier options. Think of avocado, think of the fish, oils, think of the olive oil, nuts, seeds, things like that. The reason why we need to consume lipids and why we have lipids in our body is that these are highly concentrated sources of energy. So again, thinking evolutionarily, we like eating fatty food. We like eating fatty food because that fatty food allows us to have energy in our body for a longer of a time. So we're attracted to that. Lipids are very condensed and a good way of storing energy. So that's why we end up developing fat tissue in our body if we have additional energy that we don't need to use in our body. Our body stores it as fat. Interestingly, lipids are insoluble in water. You know, water and oil don't mix, but they are often used in many forms of life due to their protective function. So many animals, like otters, do have a lipid lining on their fur, the outermost layer of the fur, so that when they go swimming, they don't just, water doesn't get sucked into that fur and they become heavy, and that would cause issues. So actually, the inner layers of the fur of otters, for example, doesn't get wet because of that lipid layer on the outside, keeping the water away. We see lipid layers also on the surface of many plants, providing them protection against UV radiation, against of animals, against of toxins, against of things that can come in rainfall. So again, lipids do serve other purposes as well than just a highly condensed energy storage. Here we see a lipid basic structure, our triglyceride. Triglyceride is made of a single glycerol and 3 fatty acid chain. And these can be broken apart during the process of hydrolysis into a glycerol and 3 fatty acids chains. So this is what would happen when we digest, for example, lipids. And then they can be combined as well, these fatty acid chains, into a glycerol during the process of dehydration synthesis. So similar terms, we're seeing them in action. But what I want us to pay attention when we talk about lipids is to a single fatty acid chain. So let's study those a little bit. And there's really two types of fats, or three, but let's start with two that we often talk when we talk about biology and chemistry of fats. We see that saturated fatty acids are made of carbons and hydrogens, and these carbons are joined to each other to form a molecule with single bonds. So there's a pair of electrons that are being shared between these carbons. And these saturated fatty acids are typically materials that are solid in room temperature, like butter, like lard. Saturated fatty acids are known with a higher elevated risk of cardiovascular diseases, so we don't really recommend for you to consume saturated fatty acids in great quantities. Instead, unsaturated fatty acids are liquid in room temperature. You can think of oils, and they are considered as a healthier option. What makes them a healthier option is actually the chemistry of these fatty acids. So rather than just having single bonds, they have double bonds, at least one or more. So in double bonds, we had two sets of electrons being two pairs of electrons being shared between these carbons. And this actually causes a physical kink in the structure of an unsaturated fatty acid. So they're considered as a healthier option. We do also see that humans, being creative creatures, have considered that, okay, well, should we try to convert some of our saturated fatty acids into some unsaturated fatty acids to make them healthier? And that's how trans fats, or what's known here in the States, I notice, as hydrogenated fats, are much more common. But we see here that through an industrial process, we're actually turning liquid things like vegetable oils into a solid form. I think margarine is the best example of that. However, we have found out, even though this was a good intention, they are not really good for you because they come with an increased risk of bad cholesterol building up. And for example, blocking some of the blood vessels and things like that. So that's why, again, reading those labels of foods that we're consuming, and if we can avoid consuming too much hydrogenated fats, probably a good thing for you. I'm not going to go into detail of this diagram, but sometimes my students ask, well, what is this industrial process? I've outlined it here. You'll see that, for example, in the process of producing margarine, we use some heavy metals to produce margarine. Then the final product that we produce is actually kind of not super pleasant looking like, so we end up bleaching it to make it aesthetically more pleasing for humans to consume. So whether you love margarine based on the knowledge of the chemistry or not, I'll leave it to you. I've shared some resources. But really the most important reason of lipids, why we need to talk about those, is that lipids are what the phospholipids are. So that what the outermost layers of the cells are. So remember, here we see a single phospholipid. Phospholipid had a hydrophilic head part and hydrophobic tail parts. And we can actually see, and we'll talk more about this later on, but we can actually see again this arrangement of these as a result of the either aversion of the water or attraction to the water. And that's how cell membranes are formed. Finally, in terms of the lipids, I want to mention steroids, mainly because steroids are made of things like cholesterol. You get all the cholesterol you need from your own body. You don't need to eat high cholesterol food, but that's what we use. Steroids, what we use to produce, for example, hormones. So they can be important for that reason. And the third macromolecule group that we need to talk about is our proteins. What's interesting, again, we can think of the sources of proteins, eggs, especially the egg whites, beans, tofu, certain meats, milk, dairy products. But what's interesting about proteins is that they don't get stored in your body. So you need to have protein around available for your body when your body needs it. If it's not there, then that's it. So that's why when you go to the gym, you might see people who are trying to grow their muscle mass. Muscle is largely made of protein, is that they consume protein drinks, protein shakes, things to have that protein available in their body when they are trying to build that muscle mass, when they're exercising the muscles, which would then be built out of protein. So we do have structural protein. If we didn't have enough protein in our body and we still went to the gym and exercised, you actually start to burn other muscles than the muscles that you're using as a source of energy. So I always tell my students that consider if you're going to the gym, it counts. But that's kind of it. When it comes to proteins, I do want you to know that there's a lot more that proteins do than just work as structural material for our body. They play an important role in metabolic reactions, as transportation mechanisms in our body, important roles in our defense system, regulating our body, and also obviously creating motion in terms of the muscles being made of protein. So proteins are important for us. If we look at the chemistry, proteins are actually polymers of amino acids. And then we have these variable groups. And again, I've provided more information about these variable groups for you as a handout that you can refer to if you're interested to dig in more. Really, I debated whether to include this picture, but I think it was good of pointing out how chemistry and the physical shape of a protein are important. So we can study or physical shape of a molecule, I guess. So we can study proteins on many different levels of detail. We can study the chemistry, or we can study how they form these sheet-like structures, secondary structures, tertiary structures, or once computers became largely available, we can actually study complex proteins in terms of how they shape, what form of a shape they take. And the reason why I have a picture of Nicole Kidman back in the day when I guess made these slides, Nicole Kidman was a big movie star and she naturally has a straight hair. Hair is made of protein. But by using chemicals to alter the chemistry of her hair, she was changing also the physical shape of that protein. So she got a perm. So really, again, what I want to highlight here is that the chemistry can dictate the shape of a protein. Sounds crucial for anatomy and physiology, doesn't it? And we will unpack that as we move further in our courses. We'll see another good example of how the shape of a protein is dictated by the chemistry. Proteins are chains of amino acids. Here we see red blood cells on a microscope level. Red blood cells typically look like these biconcave discs. So they're like round chips that someone squeezed from the middle, a little bit like donuts, but not a hole in there, but just kind of like someone would have taken a balloon and pushed it from both sides. So biconcave discs. But sometimes we have errors in the coding of these proteins that dictate the red blood cell shape, and we get something that's known as sickle cells. These sickled red blood cells take a wrong shape because of the chemistry, and that causes many consequences. And we can talk about sickle cell anemia in our BIO202 course when we talk about blood. So now that we've talked about carbs, lipids, and proteins, we just have a few more words to say about nucleic acids. But I want to pause here and highlight how your body tends to use dietary carbs as a primary means of energy. If there's no carbs available, then your body moves on to use dietary lipids as a source of energy. So this is what many of these low carb or no carb diets are based on, that if there's no carbohydrates available in body, we would start burning off fatty tissue, adipose tissue. Obviously, if you don't have carbs, you don't have lipids, say you go to the gym a lot, you exercise a lot, there's very little body fat percentage that you have. If you still keep going to the gym and you don't eat enough, you start burning structural proteins. You start burning your other muscles to just keep going. So that's something, if you're interested in nutritional sciences, to consider. The final group of macromolecules that I wanted to mention is our nucleic acids. And when we talk about nucleic acids, we're really talking about our DNA and our RNA. DNA is the genetic material that we find in the nucleus that contains instructions for your body to make all the proteins and make other things in your body. RNA is basically what we use to make a copy of the DNA in the nucleus and then transport that copy of the instructions from the DNA as an RNA to our ribosomes, which will then use those instructions to build proteins in your body. So here we see chemical structure of a single nucleotide. Many of these join together with the sugar phosphate backbone. So we have phosphate group, we have sugar group. That would be the sides of that step ladder, if you wish, of the DNA. And these side bars or mid bars that you see are our variable groups. And these variable groups are either adenine, guanine, cytosine, or thymine. In case of RNA, instead of thymine, we have uracil. You'll get to learn a lot more and have probably learned a lot more about genetics later on, so I'll leave it to that level. The very last chapter, which I'm going to review very, very briefly for the interest of time, focuses on cells. So last week we talked about tissues and how tissues were made of multiple cells on a same area that came together, shared the same function. We have also talked earlier on today about atoms and how atoms were made of subatomic particles, electrons, protons, and neutrons. And we saw how atoms could join together to form molecules. We also saw macromolecules, which were large molecules. Obviously, you know that tissues can then make organs and organ systems and organisms like a human. But what we're going to be focusing on today on this chapter 4 is on cells. And cells are described as being the basic fundamental units of life. And the reason why that is the case, that cells are the smallest unit that we can consider that is self-sustained, living on its own. So we do have many multicellular organisms like humans are that. But we have many, many, many single-cell organisms as well. And in fact, as I know that you mentioned on the discussion forum, single-celled organisms dominate our life. They're the most common form of life that we find. Other thing that I wanted to mention is that cells are by default very, very small. There are a few exceptions. We see some very long cells, for example, in our spinal cord running, but generally cells are very, very, very small. To study cells, we do need additional tools. Maybe with a naked eye, if you're really good, you can see a cell. With light microscope, we can see the nucleus and the cell's membrane. And then if you want to see any finer structures, you need to turn on to electron microscopes. I think we've spoke about the differences between light and electron microscopy last week, so I won't go into that more detail. But you remember that they allowed us to study different levels of structures. The reason why cells are so small is that once you increase the cell size, the amount of volume inside the cell increases proportionally way more than the surface area of the cell. And what cells really need is the surface area so that materials can come and exit to the cell so cell can do its functions. So we want to have as much surface area on a cell as possible. And how we do it is by keeping the cell size small. Some other adaptations how we are able to do that is by having different folds and villi on the surface of the cell as well. So the field of studying cells was field of cytology, field of studying tissues was histology. I think that's familiar for us from last time. One of the questions that I asked on the discussion forum is that, well, if we look at cells, we see that especially these animal cells have a lot of, eukaryotic cells have a lot of organelles inside them. And how did this come to be? Well, based on our best understanding at the moment, this was because a random organism entered into this cell where we really just had cell membrane, cytoplasm, and nucleus, and it just sneaked in there and ended up forming a symbiotic relationship between the cell. So both benefited. And slowly more and more cell organelles appeared, and that's how we got the modern cells that we see today. So let's do a little bit of basics. Basic cells, the first cells to evolve in the history of life were our prokaryotic cells. These are also very, very small in terms of their size, and they're very simple cells. Typically, they have just DNA floating free in the cytoplasm. And there might be some ribosomes, but that's about it. So they're very simple cells, but they outnumber all other cells in even today's world. So prokaryotic early cells to evolve, simple, not a lot of structures inside. Eukaryotic cells are the cells that you typically learn about when you go to biology classes. These evolved later in the history of life. They're much larger in their size. They have specific compartments for different cell organelles inside the cell. And the DNA is actually housed inside a closed structure known as nucleus. So you start to see how cell membranes become important in eukaryotic cells. So let's have a look now of the cell membrane. I've alluded to this a few times. So our plasma membrane or cell membrane, or sometimes we describe it as a phospholipid bilayer. I think that name really explains, because remember, it was made of phospholipids, and because there's two layers of those, that's why it's bilayer. Phospholipid is made of phosphate, glycerol, and two fatty acid chains. And now, when we arrange those spontaneously, or they spontaneously arrange, we get this bilayer, two layers of phospholipids forming the outer boundary of a cell. And that kind of was explained by the attraction to the water or avoidance of the water. We also see in this picture a protein. We'll talk about proteins in a little bit, but these membranes are really the crucial part for cells and cell structures. So the proteins that I mentioned, proteins can form in cells many different functions. They can work as channels for materials to pass inside and outside the cell, so kind of regulating that passage. This movement of materials in and out of the cells can also be intentional, so proteins work as pumps that intentionally move those. They can also work as recognizing proteins, so for example, for hormones, as key and lock mechanism, kind of receptors that detect hormones, and then based on that might activate processes. They can serve as enzymes. We talked about enzymes earlier on, assisting in many different reactions. And they also join cells together, as we'll see at the very end of the chapter content. So connecting cells together. So often when we talk about cell membrane, we describe it as a fluid mosaic model. What we mean by that mosaic part is that it's made of many different things. If you've seen mosaic pieces as artwork, it's made of little pieces, forms a bigger of a thing. That applies to cells and cell structure. The fluid portion refers to the fact that plasma membrane is by no means stable structure. It's constantly moving. So these pictures that you see are very misleading. Plasma membranes are constantly doing changes, proteins move on those, they might flip, and so on and so on. So that's what we mean when we describe plasma membranes as fluid mosaic models. I think I already spoke about how on the surface of the cell membranes, you can see these folds, villi, microvilli, increasing the cell's surface area, because that was crucial. So here we have the cell. We've now talked about cell membrane. Let's go through the rest of the structures of the cell. And notice how, by the way, how on the cell membrane you see two layers that form the outer boundary of a cell. Well, all of the insides of the cell is filled with what's known as the cytoplasm of the cell. This is a jelly-like material that's mainly water. There's some salts there as well. And that's really what gives the shape for the cell, where it keeps all other organelles on their place. I often compare when I talk about cytoplasm to my students that think of taking a balloon and filling it with water, that water would be similar to cytoplasm. It helps the cell to have its shape, helps to keep other materials inside. In addition to that, in the cell, we will see a nucleus. Nucleus is another membrane enclosed structure, and inside of that structure, we will see the DNA, the genetic material. You can learn more about different forms of the DNA and so on, chromosomes, how those condense, if you're interested, from the lecture material and from your textbook. Nucleus, funnily enough, has on its surface little holes. These are known as nuclear pores. And it is through these nuclear pores that RNA can travel in and out of the nucleus. But remember, the DNA always stays inside the nucleus. So DNA is the instructions for all things in your body, all proteins. And in order for us to utilize those instructions, we needed to first make a copy of them. And this is what RNA does. The process of making a copy of a DNA is known as process of transcription. RNA could leave the nucleus. And as it travels out of the nucleus, it finds ribosomes, and ribosomes read the instructions from the RNA and help us to put amino acids together to form a chain, and chain of amino acids is what forms a protein. This process of reading instructions from the RNA and making something useful like a protein out of it is known as translation. We're translating that information. I often offer to my students an analog that think of a DNA as a precious book in a special collections department of your library. You can't check it out, but you can go and read it. And that book then, we can take copies, we can transcribe it. You can transcribe it by hand, or you can make a photocopy of it. And then that copy you can take out of the library. That was our RNA. And you can use that copy to do something. So another analog that I give to my students, consider all of the DNA in your body as a cookery book. We never use every recipe from a cookery book. We only use those recipes that we want to utilize at that point. So we go and transcribe that recipe from that cookery book. And then that recipe we can actually translate into a delicious dish that we use. So a lot of DNA we don't utilize, we just utilize sections of specific genes from the DNA. Other structures from the cells, we see mitochondria. You might have seen mitochondria often described as the powerhouse of the cell, referring to the fact that we take chemical materials and convert them into an energy, chemical energy that your cell can utilize. We have later on found out that this happens also outside the mitochondria partially, but mitochondria is the main site of producing chemical energy for cellular activities. You can learn more about structures like cristae, these folds inside, about the interesting fact that a mitochondria contains DNA, but all of the DNA in mitochondria is inherited only from your mother. So there's a much more that we can go on to talk about mitochondria. The next structure inside a cell that I wanted to mention is chloroplast. We will see chloroplasts only in plant cells. And what chloroplasts do, they convert sunlight, sun energy, CO2, and water into sugars. As a byproduct, oxygen is produced. So really only plants can do photosynthesis, and the structure where the photosynthesis was done was our chloroplast. Chloroplast, again, a double membrane enclosed structure. You can see these disc-like structures known as thylakoid that form granules and so on. If you're interested on that level of detail, you can totally study that. Another structure inside the cell, kind of coming out of the nucleus, is a set of membranes that are folded, is known as endoplasmic reticulum, ER for short. A lot of the endoplasmic reticulum is just smooth from its surface, and it has many, many different functions. But what I want to focus is this part of the ER that has a rough surface. It has ribosomes attached to it. And it is within these ribosomes where we did convert the RNA into actual proteins, where the protein production takes place. We also see another set of membrane enclosed structures inside the cytoplasm of a cell. These are our Golgi apparatus. I often describe my students that Golgi apparatus are like a distribution center of a trucking company. So they receive materials, they repackage those and send them away. So really, Golgi apparatus is important for cell functions, for organizing materials and determining where those materials in the cell need to travel to. We also have many different kinds of vesicles, lysosomes, vacuoles inside the cells. These are important either in transporting or storing materials. And I remember that you mentioned those on your discussion post. And yes, for example, these vacuoles work as kind of like a junkyard of cells, so, especially in plant cells that are not as good as getting rid of materials as animal cells. So they end up at waste products building up in the cells there. So that might be the reason why plant cells have a limit to their lifestyle. Exactly. What else can we see inside the cell? We also will end up seeing centrioles. These are a pair of cylindrical tubes that play an important role in cell division process. So when the cell forms, the chromosomes condense and they form the spindle that pulls those chromosomes apart so that we divide the amount of DNA that has been duplicated. Centrioles play a crucial role in that. Final structure of the cells that I wanted to introduce were these very thin filaments and tubules that we find all over the inside of the cell. I've just drawn food there. These are what I often describe as the scaffolding of the cell. So they help the cell to keep its shape, keep structures on their place, but also serving as pathways through which materials can travel from one part of the cell to another part of the cell. And here I compared and contrast an animal cell. Remember, the big difference between animal cells and plant cells is that animal cells do not have chloroplasts, and their cell wall was made of that cell membrane. Plant cells instead had the chloroplast, which allowed plant cells to do photosynthesis, produce sugars. And in addition, plant cells have much thicker wall made of cellulose that gives the plant cells that rigidity so that they can stack up on each other and form harder structures, harder masses together. I think this is the last concept from the final chapter, how cells can come together. So there's few different arrangements for that. We can have these zipper-like proteins that pass through the walls of the cells on both sides, forming this tight junction arrangement, bringing the two cells together. We can also have something that's known as adhesion junctions, or sometimes described as desmosomes. These are when we have these anchoring spots inside of both respective cell, and they have then those microfilaments that come out of them, and those two parts connect together, almost like buttons of, if you think that you have a shirt where you push buttons together, clips together, so desmosomes work there. Finally, we have structures known as gap junctions. These are proteins that run through the wall of the both cells that come together and facilitate these easy channels, pathways for materials to flow from one cell to another. And really that brings us to the very end of structures, things that I wanted to talk about. I guess normally I would also talk about the process of catabolism and anabolism. In catabolism, we take large molecules and break those apart, and as we do so, we release energy. This is essentially what your digestive system does. And in anabolism, we take individual small elements and put energy and form larger molecules. So that's what's known as anabolism. We also could talk about process of endocytosis, which is basically cell engulfing, eating in materials, and exocytosis, where cell almost like vomits out material from inside it. So I think that that's all I had on mind for today for the review of these 3 chapters. I realize it's been a super long review session. I promise that I'm not planning to do this long ones. I normally try to keep them within an hour or so. I will make sure that you get a bunch of extra credit for having stuck around. Anyone who is watching this, hopefully you found this speed option to fly through it at twice of the speed. And that really brings me to the end of everything. Well, I'm glad if it was helpful. Thank you for that comment. I know there's a lot of material. I know students sometimes feel really overwhelmed about the chapters 2, 3, and 4. Remember, this is just to bring everyone to the same place. So when we start going through other systems, we all share kind of a language. So thank you again for sticking with me. I am going to be around and I'm going to post the recording as well if you have any questions, any comments. But otherwise, that's it for this session. I really see the great work you're doing in this class, and it's not going unnoticed. And trust me, I'm a big believer on extra credit. So you'll be collecting those points. So that allows you to choose if you want to skip an assignment or take it a little easier, or at least not stress as much later on the semester. So thank you again for sticking with me today.